expected to check epsilon frequently, and I think that most of you do that anyway. But that's what I know. Just so that you know. And also, as you probably have guessed already, this course will be taught in English. The lectures are in English because we want to accommodate foreign people who come to Copenhagen to study. So the textbook is in English, all announcements are in English, except the exercises. We have 6 classes of exercises and 5 of them are in English. Easier. Is it better? Thank you. So there are 6 exercise classes, and one of them, number 6, is taught in English, and the other one in English. So this way we all get, most of the time, to practice our language skills. I think this is a wonderful opportunity. So like I said, the course is a little bit different. We have a new textbook. And the content is also different, and this is somehow to integrate better 2 courses. This course, Analysis 2, and the next course, Measure Theory and Integration Theory. So we have distributed the content between these 2 courses in a way we believe is better. And the content of this course will be some measure and integration theory. And I will actually spend this hour explaining very briefly what this is about. And after that, you will see something called LP spaces and hyperspaces. And LP spaces is really some kind of function spaces which are very important in mathematics, particularly in the case where P is equal to 2, when you get a so-called Hilbert space. And Hilbert space was the main topic of the previous version of Analysis 2. Now we still talk about it, but a little bit less. And Hilbert spaces is something that you know to some extent already from linear algebra, where you were taught inner product spaces. So Hilbert space is really an inner product space, but with a little bit more. And typically these are infinite dimensional. So actually, whereas Hilbert spaces is something that fits very well with what we have seen in linear algebra, it also fits very well with something we have seen in Analysis 1, namely Fourier theory. Fourier theory naturally lives on Hilbert spaces. That's a typical, very convenient mathematical home for studying Fourier series. So this is very roughly the content of the course, and you can on Epsilon see a plan for the course, plan where for each week we have predicted roughly what we will be discussing that particular week. And you can also see the syllabus pencil for the course, the same place. Then you also before, so I will really not, there are many things about the course I will not explain here. You are supposed to look in Epsilon for practical information, but let me just very briefly mention the exam. There is a 27-hour take-home exam, same as last year. That will be handed out Thursday, November 1, I believe, and that will count for roughly 2/3 of your total grade. Then there's also a homework assignment in the middle of the course. It will be, it is due September 28th, roughly 4 weeks from now. And it is posted 1 week before, and this will count for roughly 1/3 of your grade. And I will give you more information about that later. But now you just at least roughly know that this is what you will be up against. And so this is really what I intend to say about practical information about the course. So what I want to do now is you have these 2 topics, and I really want to tell you a little bit about measure and integration theory, because what is going to happen to you is that you're going to see some set theory, we're going to talk about sigma algebras, measures, measurable functions, and the purpose of talking about all these things is to do what I will explain to you now. So then maybe you have a better appreciation of this theory that you will be subjected to. So one of the things that you have seen already in high school is the Riemann principle. And let me just briefly remind you, of course you know very well what it is. So one of the things the Riemann integral can do for you is if you have a function f from an interval a to b into the real numbers, and if the function is sufficiently nice, then you can associate an interval. And this is a real number. And the way it works is as follows. Say this is A, and here we have B, and suppose we have the function going maybe like this. Like this perhaps. This is a very dangerous thing. This will happen again, I'm afraid. Then, as you probably know, the way to do this, you divide the interval from A to B into a lot of smaller intervals. Let's say this is n and this is xn minus 1. And then what you will do is you will, so really what we want to do is we want to define the area between the x-axis and the function in the case where the function is positive. Let's only consider this particular case. And so then we divide it like this into columns. And we want to take the area of each of these rectangles. And so if you want to, they're not rectangles, that's the problem. We want to make them into rectangles. And the way to do that is that we say the roughly the height of this is we pick some point here, and then we take the value of the function of that point, and then we get an honest rectangle. So for each j, we pick a point, let's call it psi j, in the interval from, say, xj minus 1 to xj. And that is that point here. And it could be any point. Then we get honest rectangles. And then for each of them we consider this area and we add up the areas. So hence the integral is therefore roughly equal to the sum j goes from 1 to n. And then we take the area of each interval is the width of the interval, that would be xj minus xj minus 1. That is related to this. And then the height, I would like the height again. So the height here, that would be f of psi j. So this is psi 2 we have here, and this point here would be f of psi 2. So this gives you that. So there are some choices involved, and the idea is that if n is large enough and the intervals are small enough, then this number here will be close to the interval. And of course, as you will see, in order for this really to work, we want the function f has to be pretty nice. So this works. If f is nice, and nice, what would nice be? For example, continuous. It doesn't really need to be continuous, it could also be piecewise continuous. But you have seen, I'm sure, examples showing that not all functions can be explained this way. So really the problem is that if the function is wild enough, it behaves badly enough, then these numbers will not converge to anything, even with infinity. want to be able to deal with. And actually, when we look at P-spaces and Hilbert spaces, being able to deal with limits is absolutely crucial. And what do we mean by that? So for example, if I have functions n, say, that go from a to b into r, and I have a function f of x, which is simply the pointwise limit of these functions, then one could ask oneself, for example, if fn are Riemann integrable, will the limit will also be Riemann integrable. And this would certainly be one property of behaving reasonable with limits. And as we shall see, this question mark, we can cross it out and say it is not true. It is simply not true. And this is really one of the big problems with the Riemann integral, that when we take limits, it's not very compatible. So this leads us to a much more advanced let's see. This leads us to a different notion, and namely the big integral. And the way you will actually see the integral once we get to it will be slightly different, but in principle, this is precisely what happens. We take exactly the same function as before. Maybe I give myself some room. It goes from f x to a to b, and it looks say like this. This is our function, and we want again to determine the area. And what was the problem before was that there was some problem about determining the height of these columns. It was really only will define if the function behaved nicely. But let's turn everything 90 degrees around, and then take and divide the y-axis instead. Like this. And then say this is this is y I minus 1, and this is y I. Y I minus 1 and y. Okay, and then what we do is we do the following. Maybe I could even take some color chalk here, which will work. Can you see the red color? I mean, not so well. We can see. That's actually boring, but it sort of works. So we take these two values, and then we